We're switching gears now to something we refer to as inferential statistics. So in chapters 1 through 4, we were trying to describe variables, descriptive statistics. Here we're trying to infer something about the world around us. We may rely on past data, or sometimes we may rely on some mathematical theory. But our goal here is to calculate chances of future events. And our resulting answers will often be probabilities. Okay, so we're gonna spend the next few chapters playing around with probabilities, and what we mean by that is a value between 0 and 1, inclusive. So that means 0 can be a chance and 1 can be a chance. Okay, or they can be probabilities. And those are the likelihood of a particular event happening. So thinking on a number line, we have, again, inclusive, meaning that 0, if we think there's no chance that the sun disappears this year, that is a probability of 0. On the other extreme, it's almost assuredly going to rain in Florida this year, so that's a probability of 1.0. Now we often switch back and forth to from probabilities to percentages, and that's okay. So this would be 100% chance of rain and 0% chance that the sun disappears, and all the probabilities fall somewhere along this. So we can't have 110% chance, right? Even if you give 110% effort, you can't have more than 100% likelihood of an event. And so what we're going to learn is how do we decide where a particular probability or a particular how do we decide the likelihood and where it would fall along this number line? And then what can we do if we do know a probability? How can we use that or a set of probabilities? Some other terms that we'll need to kind of keep straight. We're going to refer to things as experiments. So in the example here, rolling a die, when we take one single die roll, that can be an experiment. That's the activity that we are examining. That's a very broad term, and we'll have to kind of outline what our experiment is. For example, our experiment, instead of rolling a die, might be to roll 3 dice, and that's a separate experiment. More generally, or another example, counting the number of board members. So next, outcomes are any possible result that could be from that experiment. So pretty straightforward. When we're rolling a die, you're going to observe one of those 6 outcomes, or if we're rolling 3, whatever that some 180 different outcomes or something. And then lastly, the event is a more general way or more inclusive way to talk about different outcomes that could occur. And so an event could be you observe a 1, but it could also be you observe an odd number. And so we'll have more practice with this as we go along. Some shorthand that we'll use quite frequently. So P bracket A simply is shorthand for the probability of A. And so as we crunch a bunch of different probabilities, it's going to be handy to know these kind of shorthands. So probability of A equals 0.3. And we would say that is, or we would read that as one of 2 ways. Probability of A is 30%, or probability of A occurring is 0.3. And that's that flipping between percentages and the decimal. And so A is just, I'm using that as general, but we might say the probability of slowpoke, if we refer back to the first slide there, the probability of slowpoke is 20%, or the probability of slowpoke winning the Kentucky Derby is 20%. We can also then talk about so that's a specific outcome. But if you remember, our events can be more broad. So for instance, here rolling a 3, 4, or 5, 4, 5, or 6, right? So a number greater than or equal to 4. We can sum that up as an event and say the probability of this event where x is greater than or equal to 4 is 50%. So next we're going to talk about where do these probabilities come from. And there are 3 main areas that we draw on to determine probabilities. Those being classical, empirical, and subjective. Okay, and we'll talk about each of these. The first 2, classical, empirical, we consider objective measures. So we've already talked about some classical probabilities here, where we know, based on basically on mathematical theory, what the underlying probabilities would be, right? And so here we have, we can simply calculate it as the number of outcomes or favorable outcomes or outcomes that would count as being part of the event divided by the total number of outcomes, right? So again, we're all probably quite familiar with rolling dice and playing Catan or something and understanding the probability of rolling a certain, rolling a 7 on 2 dice. In this case, the probability, with just 1 dice, we'd have 1/6 probability of each of those events. But again, more broadly, we already calculated, we knew quite naturally that the probability of greater than or equal to 4 was 50%, because that includes 4, 5, and 6. So 3 favorable outcomes out of a total of 6 possible outcomes. Now, when we think about the full set of probabilities, 2 concepts that we'll return to, which we've seen in the past, are the ideas of mutually exclusive and collectively exhaustive. Okay, and remember, we covered these when we talked about a frequency table, right? And so all of our data had to fall into somewhere on the frequency table. Similarly here, we need to have all of the possible outcomes be accounted for. And so so the logic here is very similar to the frequency table. So the occurrence of one event means that none of the other events can occur. So when we break down, if we want to talk about, all right, what is the probability that it's 4 or greater, we can't also have in that same possible outcomes be the probability of 5 or less. So they need to be mutually exclusive. If we want 4, 5, or 6 to be 1, or greater than or equal to 4 to be one possible event, then the other event or events need to not include those outcomes. And again, similarly, and kind of on the flip side, we need to make sure that an event occurs. So again, if we're talking about 4, 5, or 6 or greater than or equal to 4, then there's also a chance, or there's a set of outcomes where it could be not that, right? And so it could be 1, 2, or 3, and we could do 3 or less, or we could do 1 and a separate one for 2 and a separate one for 3. But we do need to make sure that every possible event, or whatever the outcome is, falls into one of the events that we're looking into. So that was classical, where we're relying on the underlying theory to calculate the probability. We can also rely on past data. So empirical probability, we look at what has happened in the past to get a sense as to the probability of event happening in the future. Okay, so we would look at the number of successful flights compared to total flights, right? Hopefully this is not maybe this is a paper airplane. Hopefully we're not only at 98% successful flights. But we would rely on that past information as to whether or what the probability of a future success is. So we see this a lot in say sports, right? So we have a good sense as to, you know, the likelihood of LeBron James hitting his next free throw. You know, probably somewhere in 76% or something, right? If we look at his past performance, that gives us good insight into the future. And one thing we rely on here is that over a large number of trials, that the true value is going to, or that the empirical probability, so the results over a large number of trials are going to approach what we would consider the true probability. So there's some true probability that LeBron hits this next free throw, and given that we've seen so many of his past free throws, we think that his past free throws approach what the actual true probability is. Yeah, so sometimes we don't have some theory to base that probability on, but we do have that past experience. So again, the free throw percentage, or, you know, there's no theory that tells me what the percentage that my chance that my stomach will be upset the next morning, but given past experience, enough times eating spicy hot wings, I have a pretty good feel that it's a quite high percentage. Sometimes we don't have a theory, and we don't have a mathematical theory or a way to exactly calculate that classical percentage, and we don't have enough past data, or this situation is new or unique enough that we don't have past data, and so we have to rely on a subjective concept of probability. Okay, and here we're going to draw upon different information to try to narrow down that probability. So a classic example is the chance that the Patriots win the Super Bowl next year. Now, we do have past data. What is that? They've won 5 out of the last, 20 Super Bowls or something like that. And so if we relied simply on empirical probability, we might say they have a 25% chance of winning the Super Bowl. But there's probably other information that makes this a unique situation, right? So they no longer have the who some consider the greatest quarterback of all time. So he's no longer on the team. So the past events may not be applicable here or as applicable, right? So in a similar sense, yes, we know LeBron has hit 77% of his past free throws, but let's say he has a broken hand and has to shoot with his opposite hand. So that the uniqueness there means that we don't necessarily have the past data to rely on. Similarly, likelihood that the budget deficit will be reduced in half in the next 10 years. We don't have any data to rely on. We do have years of U.S. budget deficits, but the uniqueness of every year makes it tough to rely solely on those the past data. Now, that doesn't mean we don't take that into account, but we often adjust from there. So we have two kind of branches of probability: objective and subjective. And within the objective, there's the classical and empirical. Now, again, sometimes these kind of mix, or we use one to kind of test the other, and vice versa. But this is a good way to kind of outline the fact that we're going to sometimes need to approach probabilities from different avenues. Okay, so we'll be back on some specifics as far as how do we calculate various probabilities and play around with outcomes and understanding those.